Hey guys, making a key here for the momentum simulations that we did before break, but I realized I hadn't put it up there, so I wanted to do that for you to make sure that as you're looking this stuff over, that you've got a good understanding of everything. So the first one was with the Fish Catch Interactive, and so you just had to get some data on the speeds and the masses of these fish. So if we look at one of these, we can begin activity here and any one of them. So as this goes, we got the masses of the little fish was 15, 45. So the velocity was 80, and then it went down to 20. So let me minimize this. We'll come back. But so this little fish was 15, was 45, 80, and 20. So a couple things to note here is as you went through these, they always slowed down. All right, so that's a key thing to notice. But also, and we talked about this in class, but just you may not remember or you may have missed it. But what is happening here is, and I'll repeat it, but at first the little fish is the only one with momentum. And then as the big fish eats it, they both have momentum. And so I don't know why that's numbers like that. But now that momentum is for both of them. And so let's go and do a different one just so you can see it with the numbers. So what's important for you to realize is a couple of things. Is one, the velocity of both fish is the same because they're together. It's like an inelastic collision that we did. Even more importantly, you see the total momentum before is equal to the total momentum after. And that had to do with the bigger concept of momentum conservation. So when we go back here and look at this, you guys filled out all the data, but in terms of the questions here, how does the final speed compare to the initial speed? So that the final speed is always lower in this situation, and that's because there's more mass that's moving. So this is because the total mass that's moving is greater. So if we have the same momentum, if picture two objects, like let's say a car and a truck. If they have the same momentum, then the car has to be going faster. So that's the same as like the little fish before is the only one moving, so that has to be moving faster than the two fish together, two fishes. So does the total momentum change from before and after? No. And well, we don't need a comma there, and that's because the total momentum is conserved. Before the collision, all the momentum is from only one fish. Why is that? And that's because the other fish isn't moving. So because it wasn't moving, it has zero momentum. If the fish were moving to the left, how would its momentum be different? And so in that case, the momentum would be negative. So because direction matters. And so I realized too, also, if you're in first and second hour, you had a couple different questions. So I updated these. I thought they were better than the ones after looking at first and second hour answers. I thought they were a little confusing. So I changed them to these, but so you can make that mental adjustment, I think. And then here are the exploding carts. So with this one, different situation, same key concepts here. So what we want to do is get some data from that. And I'm just going to just do one again for video sake. So if we look at this, and let's just we'll give this cart a mass of 1 kilogram and this cart a mass of 2. So we can see, so we'll just compare those. Then we explode them. That's a little plunger that's in there. And you can see the red cart was slower, so it took longer to get over there. So this was 1, 2, and then 30 and 15. So when we go back, and one thing that happened, if you note, red is here on the right, and red is on the left here. So I apologize about that. So this was 2, and this was 1. Red cart was 15, the blue one was 30. So a lot of kids had those backwards because they were opposite of what it is in the simulation. So if you made that mistake, that probably accounted for some confusion. So apologize about that. But that data there is really important for us as we get down here. So we'll come back to it, and it works the same for all of them. So individual momentum of the red cart before, it wasn't moving. So this was 0. And of the blue cart before was 0. So neither one of those were moving. And so then that makes, if they both have a momentum of 0, the total momentum before is 0. And a lot of kids miss that, and we're doing some calculations and stuff. So a little more conceptual, and you guys could all tell me if something isn't moving, it has 0 momentum. And so I think we just maybe got confused in the midst of the simulation. So, you pick 3 trials. I'm just picking trial A here, just for our purposes. And post-explosion momentum of the red cart. So how much momentum did the red cart have? Well, the red cart was 2 kilograms going 15 meters per second. So it had 30 kilogram meters per second, and that one moved to the right. And the blue cart, so to figure out its momentum, mass times velocity, 1 kilogram, 30 meters per second. So 1 times 30, that was 30 kilogram meters per second to the left. And direction here is what really makes a difference. So 5 says, how do the direction of these compare? And they're the opposite direction. And then ideally, you know that because if these are vectors, and the direction matters, if we were to add these, we'd have 30 kilogram meters per second to the right, that would be positive, and then to the left would be negative. So what's the vector sum of these? It ends up being a positive 30. Oops, don't do it like that. Positive 30 plus a negative 30, which equals 0. So that was a key thing about this simulation. What was true about the impulse on each cart in each trial? So here you couldn't calculate force times time. We didn't have that information. But because the impulse is the change in momentum, the impulse was equal on each cart. So here's what that means, and that's a bigger conceptual one, is these things explode apart. The force on them, because of Newton's third law, has got to be equal, right? One cart can't push the other cart for more or less. And then the time that they're pushing has got to be the same, right? I can't push you longer than you can push me. So if force and time are the same, the impulse has to be the same. Another way of thinking about that is they both changed momentum by 30, right? One just went to the right and one just went to the left. So if their change in momentum was 30, then the impulse had to be the same on them. And then was the impulse the same on each cart in a specific trial? I shouldn't ask that question again. It seems stupid now, but yes is the answer. That's the same as this right here. The impulse was equal on each cart. So I apologize about that. I must have thought it was good. So that is the momentum simulations. So when you're looking that over, let me know if you do have more questions about it, and we can talk about it.